wouldn't say it's any harder than chapter 4, but it does have a lot of content in it, just like chapter 4. Okay, so it's going to be a lot of information, and it just kind of builds. So I do have some warm-up on here, but I'm not going to turn you loose on it on your own because I want us to speed up and go quickly through it. So I'm just going to do it with you. If you want a compass to practice with me, you can. You can go grab one real quick. In this section, you will be talking about doing constructions, and it's important that you remember what we did in chapter 1 when we did these constructions, okay? So if you have a compass, grab one. If you don't have one and you want to practice along with me, go grab it. But I'm going to remind you how to do these, okay? Maybe. Here we go. So first one is a perpendicular bisector. Back in chapter 1, if we wanted to construct a perpendicular bisector, can anybody remind me what I do with my compass if I want to do a perpendicular bisector? Say it again, Ivan. Okay, so I'm going to put my point. Which letter did you say to put it on? A. So he said put your compass point at A and make an arc. And he said before B, can it be really small? So can it be that small? No. So how big does it need to be? Okay, so bigger than at least the midpoint. It can be as big as you want it to be as long as you have room on your page. But just make sure it's bigger than the midpoint. So Ivan's right. We're going to put it at A, sliding. And we're going to make an arc that's really big that goes above and below. You can make a full circle. I just usually don't because it makes it a little bit messier. Okay, once you go to point A and you make that arc, then what do? Do the exact same thing for point B and don't change your radius. So we go to point B and we make an arc. And you should have notes on this somewhere back in chapter 1 where we did these constructions. So you make an arc above and below. All I did was go to point A, make an arc, go to point B, make an arc, never changed my radius, and I made sure that it was at least wider than the midpoint. You have to make sure your arcs are big enough that they do intersect, and they have to intersect twice, once above and once below, so that you have 2 points to connect with a ruler. And then you just use your straight edge and connect those points. Everybody with me on how to do a perpendicular bisector? Okay, back in chapter 1, we didn't call it a perpendicular bisector. In chapter 1, we just called it a segment bisector. And all we talked about was how it split the segment into 2 congruent parts. And it made this point right here, what did we call that point? The midpoint, right? We never talked about it being perpendicular. But if you've done it correctly, it is not only just a bisector, but it is also a perpendicular bisector, which is what this section's all going to be about. And that means that it also makes a right angle. Okay, so it's not a new construction. It's the same construction we've always done, but it is a perpendicular bisector. Okay, second one that we did in chapter 1 was an angle bisector. So on your paper, if you want to follow along with me, you can make yourself an angle. Does anybody remember how to do an angle bisector? Okay. Okay, so I'm going to give that a letter A. Go ahead. Sorry, Jacob. Okay, very good. So I put my compass point at the vertex and I make an arc that intersects both sides of my angle or both rays. I'm going to go ahead and label those intersection points just so I can talk about them. So I'm going to call one of them B and one of them C. And then what did we do from there? Very good. So you take your compass point after you go to A and make an arc, and you just repeat that process at both points B and C and find out where they intersect. So you put your compass point at B and make an arc, and then put your compass point at C and make an arc. And you're looking for where they cross. And once we find where they cross, where do we connect that point back to? The vertex A. And that gives us an angle bisector. Which, remember, splits your angle into two congruent parts. Any questions on reviewing those constructions? Okay, so that is where we're going to start this lesson, is talking about perpendicular bisectors and angle bisectors. And then in section 5.2, we're going to take these two concepts and we're going to apply them to a triangle. So in a triangle, how many sides do you have? 3. So that means you can draw in 3 perpendicular bisectors. How many angles are in a triangle? 3. So that means you can draw in 3 angle bisectors. And so when we get to section 5.2, we're going to take what we learned in 5.1 and apply it to a triangle times 3, because we're going to have 3 sides and 3 angles. Okay? Something else you're going to have to use in this section is the midpoint formula. So can you guys remind me, actually midpoint and slope. So let's start with midpoint and then we'll talk about slope. What's my midpoint formula? No minus? Okay. Exactly. Remember that another way to think of midpoint is it's the average of your x's and the average of your y's. And when you average, you add and divide by how many you have. Okay? So if I want to find the midpoint here, we would have 2 plus negative 4. And we would divide that by 2. And I really shouldn't put plus a negative, but I'm going to do it just to remind you that the formula is adding. Okay? And then we have 8 plus 6 divided by 2. So what will that reduce to? Good. So negative 2 divided by 2, which is negative 1. And 14 divided by 2 is 7. Any questions on calculating midpoint? Okay. And then slope. Remind me how I find the slope given 2 points. What's my slope formula? Careful, you've got it backwards. There you go. Change in y over change in x. And how do I calculate change in y? Good. So it's the difference in our y values, y2 minus y1. So the change in y over the change in x, x2 minus x1. That's our slope formula. Again, you could graph them and count the rise and count the run, but that's not always going to work when you get to some ugly numbers or fractions, and when you get into calculus. You don't want to always be having to graph something to find your slope. You want to be able to use your slope formula. So at this point, if we plug these in, we would have 6 minus 8 over negative 4 minus 2. And what does that reduce to? Bless you. Negative 2 over, I'm sorry, I didn't hear you. Negative 6. And then what does that reduce to? Which reduces to? There you go. So positive 1/3. A negative over negative is a positive, and then that reduces to 1/3. Any questions on slope? Okay, all of these things are things you need to know for this chapter, so super important that you can work all of those problems. So we're going to move right into this section 5.1 is going to talk about 2 theorems, the perpendicular bisector theorem and the angle bisector theorem, which is why we started with constructing each one of these. Okay, so I'm going to label up here on the board, this is perpendicular bisector, and this is angle bisector. Okay, and then we're going to talk about what these theorems say. So this is the construction for each of those. We will not have locus. I will not put that on the vocab test. I know this isn't on your notes, but if you want to make a note to yourself that locus is not on the vocab test, when you look at the end of the chapter and all of the words and you're making yourself a Quizlet and you're studying, locus will not be on your vocab test. okay? Locus, just so you know, is just a word that means the set of points. So anytime you would want to replace the phrase, the set of points, you could replace it with the word locus, but I'm not going to do that. So we won't worry about that. We will talk about equidistant, though. All right, so when they tell you in the directions that something is equidistant, you need to know what that means. So when a point is the same distance from two or more objects, that point is said to be equidistant from those objects. So equidistant just means the same distance from two or more objects. In other words, I could be equidistant to Marissa and Marlene if I am the same distance from them, right? So anytime they tell you equidistant, same distance. All right, first theorem, and again, this section is really just two theorems, the perpendicular bisector theorem and the angle bisector theorem. So we're going to start with perpendicular bisector theorem, and then of course there is a converse to it. So perpendicular bisector theorem says, if a point is on the perpendicular bisector. So when we look at this picture, first of all, what is the line that is the perpendicular bisector? XY. Notice it's perpendicular and it's bisecting. So this line right here is a perpendicular bisector. Everybody see that? Over here on the board, I'm going to go ahead and use a green line as well. So this is my perpendicular bisector. Okay, and so I'm going to represent here what the theorem says. So the theorem says if you have a point on the perpendicular bisector, sorry, I'm going to get a different color. If you have a point on the perpendicular bisector of a segment, then it will be equidistant from the endpoints. So what that means is any point, if I pick a point on the perpendicular bisector, this theorem says that it will be equidistant to the endpoints. So this distance will be the same as this distance. Does that make sense? Be careful, it can be any point, and it doesn't mean that they're all the same distance. So I could have a point, let's say, way down here. It's on the perpendicular bisector. The distance from it to B is the same as the distance from it to A, but it's not the same as the purple distances. Okay, so it's not saying that any point is equidistant to the endpoints anywhere. It's saying that point is equidistant to the endpoints. Okay, and it can be any point on that line. So when you look at our picture here, that would mean that AX and BX would be the same distance, equidistant. Any questions there? Okay, the converse. So here's how I remember the difference between the two. Perpendicular bisector theorem, the picture is going to show you that you have a perpendicular bisector with a perpendicular mark and bisecting marks. So when you look at the picture, they show us that it's a right angle, they show us that it's been bisected. When you look at the converse, it does not show you a right angle or bisecting marks. Would you agree? Okay, so you don't know that you have a perpendicular bisector. The converse says, if a point is equidistant from the endpoints, so now we're going backwards. We look at the picture and we notice AX is congruent to BX. These distances are equal. If that point, X, is equidistant to the endpoints, then that point X must be on the line that is the perpendicular bisector. So what we can conclude is that XY must be the perpendicular bisector. So XY is going to be perpendicular and it's going to bisect that line. Do you see the difference between the original theorem and the converse? And again, the way I remember it is the original theorem gives you that it's a perpendicular bisector, hence the name. The converse does not. The converse, that's what you're concluding. So the converse is going to say, yeah, I'll just go ahead and go. This point is equidistant to the endpoints. And so you're concluding that this must be perpendicular and bisecting. What you're really concluding is that XY is a perpendicular bisector. Yes, ma'am. Yes, so depending on which theorem you're using. So if you're trying to conclude that the distances are equal, then you would be using the original theorem. If you're trying to conclude that this line is perpendicular and is bisecting, then you would be using the converse. Okay. All right, this chapter will be a lot less proofs though, by the way. It's not going to be proof intensive. Chapter 4 was our biggest proof chapter. And second semester, you'll see that we do less and less proofs and more computations. So we're going to be doing a lot more things with like volume, surface area, similarity, things like that. There will still be proofs. We're not done with proofs, but there will just be less proofs, okay? All right, so we're going to use that theorem, and now we're going to apply it to just solving some pictures, trying to find missing measures, missing angles, whatever's in the picture. So in this case, they want us to find TU, the distance from T to U. So when I look at the picture, first thing I would ask myself is, do I have a perpendicular bisector? Yes. Which line is the perpendicular bisector? UW. And so the theorem, the original theorem, just said then that means U is equidistant to the endpoints T and V. So what could I write down as an equation? Exactly, Cooper. Good job. So I can set those equal to each other. 3x plus 9 is equal to 7x minus 17. And then we're just going to solve for x and plug it back in to find TU. So if I solve for x, I can subtract 3x. Gives me 9 equals 4x minus 17. Add 17. And that gives us 4x equals 26. And then divide by 4. And what does that give us for x? Very good. 6 1/2. Be careful with the directions though. You want to plug that back in and solve for TU. So now we're going to go over here to TU and plug it in. 3 times 6 1/2 plus 9. Because that's what TU is equal to, is 3x plus 9. What's 3 times 6 1/2? Say it again. 19.5 plus 9 gives us what? 28.5. Any questions using that perpendicular bisector theorem? Okay, and that was the theorem, not the converse, right? Because they gave us that it was a perpendicular bisector. All right, moving on. Same idea here. These will get pretty easy. They're not super difficult as long as you understand the theorem. So read through your directions here. And then I would always label my picture, so they're telling me that L is the perpendicular bisector of DE. So they've already shown me the perpendicular part, but what else could I mark? Exactly. It's not only perpendicular, but it's also a bisector of DE. So I can mark those DF and EF pieces congruent. And then they tell me that EG is 14.6, so I could label that in my picture. And the question is, what is DG? So using the theorem that we just learned, if this is a perpendicular bisector, then G is equidistant to the endpoints. So that means these two sides are equal, so DG is just 14.6. Was that the theorem or was that the converse? The theorem, because they gave you that it is the perpendicular bisector. So if they give you it's a perpendicular bisector, that's the perpendicular bisector theorem. Do I put a line segment above DG? No. Never when you're giving me what it's equal to in terms of a number, because that's distance. Okay, good. All right. This is really important for what's next. Sorry. It says, remember that the distance between a point and a line is the perpendicular segment. In other words, if I have a line and I have a point, and I want to know how far is point A from that line, I could draw all kinds of lines from A to that line, right? But which one would give me the shortest possible distance? Okay, so one that makes a right angle that is perpendicular. So when we talk about the distance between a point and a line, we're always referring to the perpendicular segment. Okay, you would never measure distance diagonally. I wouldn't say how far am I from here to the wall and then walk towards Denise. That would be a lot longer, right? I would walk straight ahead and make a right angle and measure my path, and that would give me my shortest distance. Okay, so that's going to lead us to the second theorem in 5.1, which is the angle bisector theorem. So now we're back to angle bisector. We know how to construct it. We're going to learn what the theorem says. So the theorem says, again, that you have to have an angle bisector. So if a point is on the angle bisector, so it starts with a picture where you can see that you have an angle that is being bisected. That means that PC is the angle bisector. Do you guys agree? Okay, so this theorem simply says if you have a point on that angle bisector, it will be equidistant to the sides of the angle. And when they say equidistant, that has to be drawn perpendicularly. And that is key. So the distance from C to the sides of the angle, they have to draw those distances so that they're forming right angles. If they're drawn so they're forming right angles, this theorem says that those distances will be the same. And again, it could be any point on that line. I could pick another point that's on that ray that's my angle bisector, and the distance from it to the sides of the angle will be the same. But again, that distance has to be drawn perpendicularly. Here's how they'll trick you. Well, this is not a very good marker. So do you have an angle bisector? We do, right? Because we've got arc marks saying that these are congruent, right? So we do know that this is an angle bisector. This is a point on the angle bisector. It should be equidistant to the sides, right? But is this distance going to be the same as this distance? No, because it's not drawn perpendicularly. If this had a right angle on it, then we know it's 7 because those distances will be equal. But they could draw that distance any way, and then they don't have to be the same measure. So be really careful when it says that it's equidistant, has to be drawn perpendicularly. Does that make sense? Questions? Okay. So then on my picture up here, I'll mark that. Same idea. Any point on this angle bisector will be equidistant to the sides of the angle, drawn perpendicularly. Okay, the converse. Converse is just going to go backwards. You're not going to know that it's an angle bisector. So now you have an angle. You do not know that it is split into two congruent parts. There's no markings here to indicate. But you have that the distance from a point on this ray is the same as the distance from that point to the other side. So if they give you the distances are the same, what can you conclude about AP? It's the angle bisector. So the converse would say we can conclude that ray AP is an angle bisector, which means we would now know that these angles are congruent. Okay, so that's what they're showing you over here. If a point is on a ray and it's equidistant to the sides, then that PC must be the angle bisector. So now we can mark these two angles congruent and say that those angles are congruent. Questions on perpendicular bisector theorem versus angle bisector theorem versus their converses? Okay, again, let's look at some problems. So here's an example. First thing you want to do is look at the picture and ask yourself, what are they telling you? What does this picture show me based off of markings? Careful, perpendicular bisector. Okay, it is going to be an angle bisector. What is the angle bisector in this picture? Say it again. Km. So what they're showing me is that ML, that distance, is the same as MJ, that distance, right? And that point M is equidistant to the sides of that angle. So that means that Km has to be an angle bisector, which means this angle has to be congruent to this angle. Is that the angle bisector theorem, or is that the converse of the angle bisector theorem? Converse, because they did not tell us it was an angle bisector. They told us the distances were congruent. We concluded it must be bisecting the angle, okay? And so what would we write down to solve for the measure of the angle? 3a plus 20 equals 2a plus 26. All right, then we can just solve that simple algebra problem. Subtract 2a and we get a plus 20 equals 26. Subtract 20 and what is a? 6. But that's not our answer, right? Plug it in. We're looking for MKL. MKL, that's this angle right here. So we have the measure of angle MKL will equal 2 times 6 plus 26. What's 2 times 6? 12 plus 26? 38 what? Degrees. Don't forget your degree symbol and don't forget your little m for measure. Any questions on that one? Okay. Okay, if we go over to the back. This is also another really easy one. It says, given that YW bisects angle XYZ. So they're giving you that this is an angle bisector, right? YW, which is this line, is bisecting angle XYZ. So what does that tell me in the picture right now? What could I mark?
Oh, that XYW is congruent to CYW.
Exactly. So it's telling us that that angle is being bisected, so it's being split into two congruent parts. What does this theorem tell us then? If YW is an angle bisector, what do we now know?
Oh, that XW is equally congruent to CW.
Exactly. XW is congruent to ZW, that the distance from W to the sides of the angle is the same. Okay, so then look at what they tell you. WZ is 3.05, and all they want to know is what is WX. So what is WX? So the problem is not mathematically hard. It is just do you understand the theorem and what to mark and what you know from the theorem. Okay? Any questions there? Okay, the next one's a little bit more challenging in that you need to understand some vocabulary in the problem, but other than that, it's not hard either. It says S is equidistant from each pair of suspension lines. So you need to know what are suspension lines. So when you look at the picture here, they're telling you that S is equidistant from the suspension lines. What are the suspension lines in the picture? Okay, so the lines coming from the parachute, PQ, RQ, or SQ, right? All of those lines that are coming down from the parachute. So if S is equidistant from PQ and RQ, the biggest mistake I see is students say that means PS is congruent to RS. But remember, what does the word equidistant mean? When we draw distances, how do we draw them? Perpendicularly. Is this drawn perpendicularly to this line? No, and we don't know, but it doesn't look to be, right? So what we know is that if they tell us S is equidistant from this suspension line and this suspension line, then we could draw a line that is perpendicular, and we could draw a line that is perpendicular, and those distances should be the same. Is everybody with me there? S is equidistant from the suspension lines, is what's given to us. And but distance has to be drawn perpendicularly. Again, I would not measure my distance over to this wall by walking diagonally. I would do it perpendicularly. So if they say the distance from S to this line, they mean it perpendicularly. Are you guys with me? Okay, so knowing that, it says, what can we conclude about ray QS? So what does that mean about this ray then? It's not a perpendicular bisector. It's an angle bisector, because if the distance from the point to the sides of the angles are the same, then that means the line that that point is on must be an angle bisector. So QS is an angle bisector. Again, look at your two pictures here. They're giving us this information, so we can conclude that this is an angle bisector. Does that make sense? The mistake I usually see is students wanting to mark SP congruent to SR, and then they try to say that it's a perpendicular bisector. But that's not what equidistant means. Denise? So equidistant means that a point, if it's equidistant to two things, has the same value or same distance from that point to the two things we're talking about. So going back to this problem, when it says point S is equidistant from the suspension lines. So I'm going to call this S. The suspension lines are here and here. The problem is that a lot of times students want to think the lines that are drawn in the picture are the ones that are equal. But we said when we draw distance, just like when I said I wouldn't walk to you to measure my distance, I always go perpendicular. So if they say that this point has the same distance, equidistant, from this line and this line, then when we draw that distance, we have to draw it so that it's perpendicular to get the shortest distance. And we have to draw it so that it's perpendicular to get the shortest distance. And then equidistant means they're the same distance. Does that make sense? Okay. Other questions? All right. Last problem you see, I believe, requires some graph paper. Am I correct? Okay. Grab a piece of graph paper. Okay, I'm going to tell you right now, guaranteed you're going to see this question on your test. Guaranteed it's going to be on your homework, on the review. Make sure, make a note to yourself, you better go back and study this. This is day 1 of chapter 5. By the time we get to the review day, that's going to be a long time since today. And you're going to forget how to do this. You're going to need to go back and study it, okay? So first of all, it says write an equation in point-slope form. This goes back to chapter 3. What is point-slope form? Very good. So y minus y1 equals m times x minus x1. You will have to know your two forms of writing equations of lines back from chapter 3. There was point slope and then there was slope intercept. This one says point slope. You want to write an equation in point slope form for the perpendicular bisector. So your equation is supposed to be of a perpendicular bisector, like here. It needs to be the perpendicular bisector of this segment that they give you the points for. So if you go to your graph paper, you can graph those 2 points. So graph your line segment. Where I see a lot of students make a mistake is they write an equation for CD. Did it say write an equation of the segment CD? No, it said write an equation of what? Of the perpendicular bisector of this segment CD, right? So basically what that means, if you think about up here on the board, they're giving us the black line and they're wanting us to come up with the equation for the green line, the perpendicular bisector, right? Okay, so if it's a perpendicular bisector, think about some characteristics of it. Number one, we already talked about, where does the perpendicular bisector cross the line segment? At the midpoint, hence why we did midpoint in the bell work. So if we want to know a point that's on our line for our perpendicular bisector that's going to go through this line segment, we know for sure one point on that line is going to be the point where it crosses the midpoint. Does that make sense? So the first thing we need to do is we need to calculate the midpoint of CD. And that is going to be our coordinate x1, y1 for our formula here, y minus y1 equals m times x minus x1. Because that is a point that's on this line. Okay, so let's calculate the midpoint of CD. Midpoint, remember, is the average of your x's. So you add and divide by 2, and the average of your y's. So you add and divide by 2. So start with your x's here. What are we going to add first? 6 and 10, so 6 plus 10. And then what are we going to add for the y's? Negative 5 and 1. So we end up getting for our point x1, y1, when we simplify, what is 6 plus 10 divided by 2? 8. And negative 5 plus 1 divided by 2? Negative 2. Okay, so that's going to be your x1 and your y1, but be very careful, just like we talked about back in chapter 3. Okay, I'm going to take a break in just 1 second. But once you find your x1, y1, be careful. A lot of times, you guys, in chapter 3, plugged the 8 in first, but the first letter is the y value, right? So be really careful. This is going to be y minus what? Negative 2, so it's going to be y plus 2 equals, we still need to find our slope. We haven't found that yet. And then x minus 8. So the first thing you do to write an equation of a perpendicular bisector is you find out where's the bisecting point. What's the midpoint? Once you find that midpoint, that is your x1, y1 for your equation. So we know for sure that we have a point at 8, negative 2, which is our midpoint of our line segment. And now we want to come up with the equation that's going to go through that point perpendicularly. So what do we know about lines that are perpendicular on a graph? Okay, they do form a 90-degree angle, but what we need for the graph is that the slopes, both of you are saying the same thing, the slopes are what? Opposite reciprocals. You have to flip them and change the sign. So the second thing you know is that you need to find the perpendicular slope, which means to remind yourself that they have the opposite reciprocal slopes. Again, stuff we learned in chapter 3. Okay, so you need to find the slope of the line they've given you, and then you need the opposite reciprocal of it. So let's find the slope of CD. So what is the slope from C to D? You've got it on your graph. It's probably easy to just count the rise and count the run. Okay, so when you count, before you simplify, what was your rise? Look at your graph, count your rise from C to D. 6, right? And then what's your run from C to D? 4. And so you went up, which is positive, you went right, which is positive, and 6 over 4 reduces to 3 over 2. Okay, 3 over 2 is the slope of CD. That's not the line we're writing the equation for. We want the one that's perpendicular. So we need our slope to be what? Very good. Opposite reciprocal. Flip it, change the sign. So negative 2/3. So then you're just going to plug that in for your slope to write your final equation. So your final answer would be y plus 2 equals negative 2/3 times x minus 8. It said to put it in point slope form, so you do not simplify. You leave it in point slope form. Questions? So big idea, just to clarify. We wanted to write an equation of a perpendicular bisector. First thing we did was we looked at the segment that we wanted to bisect. We found the midpoint of that segment. We used that to represent a point that would be on our line because it's going to go through the midpoint. Then we wanted our line to be perpendicular, so we said, okay, it should have the opposite reciprocal slope. We found the slope, we flipped it and changed the sign. We plugged in our point for x1, y1, and we plugged in our slope for m. Questions anywhere in 5-1? Okay, I'm going to answer this message to my dentist, and then we'll do 5-2, so give me just a second. Okay, hopefully he'll text me back again. All right, so let's look at 5-2. So 5-2, like I told you to start with, is going to take these same two ideas, but now put them in triangles, where there's 3 sides we could perpendicularly bisect and 3 angles that we could bisect. Okay, so first of all, we already said this, so I'm going to skip that. Want to clarify about perpendicular bisectors. So when we talk about the perpendicular bisector of a side of a triangle, so everybody look up here and you may want to draw this in your notes. Draw yourself a triangle. When you create a perpendicular bisector, and again, you could use your compass to do this on each side of your triangle. When you do that, it's going to pass through the midpoint. So let's just say I estimated this is where my midpoint is. And it's going to form a right angle, right? So I want to remind you that a perpendicular bisector does not have to go through the vertex. That was not the definition of perpendicular bisector. A perpendicular bisector goes through a side so that it is perpendicular and it bisects the side. It could, oops, my bad. It could go through the vertex. It just depends on what kind of triangle it is. So for example, if I had an isosceles triangle, where this side's congruent to this side, and I found the perpendicular bisector of the base, it will end up going through the vertex because it's isosceles. But that is not always the case. So I want to make sure you're clear that a perpendicular bisector does not have to go through the vertex. It has to be perpendicular and it has to bisect the side. Okay? Can go through the vertex, does not have to. All right. So when we're talking about these two things in a triangle, we're going to be creating 3 perpendicular bisectors, 3 angle bisectors, and when 3 or more lines intersect at a common point, those lines are said to be concurrent. When 3 or more lines intersect at a common point, they are said to be concurrent. In other words, if you take the line here that is made by the ceiling and this wall, everybody see that line? Okay, if you take the line here that's made by these 2 walls going up, everybody with me which line I'm talking about? If you take this line that's made by the ceiling and this wall, do you see how there are 3 lines coming together and intersecting? And they intersect at that common corner point up there in the ceiling, right? So those 3 lines are said to be concurrent because they intersect at a common point. That's what they mean visually in this room. On your paper, you could draw 3 lines that all intersect at a common point. If they intersect at a common point, they're said to be concurrent lines. That's important. Then that point where they meet, over there in the corner or right here on my paper, that point is called the point of concurrency. It's the place where all 3 lines intersect. The point where they intersect. So the lines are called concurrent lines. The point where they meet is called the point of concurrency. And this is probably the hardest part of chapter 5 coming up. You are going to learn today and next week 4 different points of concurrency. You're going to learn what kind of lines make that point of concurrency. And you're going to have to keep straight the theorems that go with each point of concurrency. Okay, so right now you've already got 2 theorems about lines, perpendicular bisectors and angle bisectors. We're getting ready to learn some theorems about points of concurrency. Everybody following me what we're talking about? Okay, so when 3 lines intersect at a common point, the lines are concurrent, the point is called the point of concurrency. So we have not yet done this. Right now on your paper, do this with me. I want you to draw a triangle, and then we're going to estimate in all 3 perpendicular bisectors. I'm not going to take the time to construct it with the compass. Let's just estimate, okay? So on each side, you're going to estimate where you think the midpoint is, and then you're going to draw a line that looks like it's making a right angle. Please do it quickly. Don't take time to make it perfect, okay? So just quickly sketch a perpendicular bisector through one of your sides. Then do it to the next side. So pick a point where you think it looks like it's the midpoint that splits your side into 2 congruent parts. And then draw a line that looks like it's making a right angle at that point. Do you see how I'm just sketching that on each side? Then go to your last side and pick a point where it looks like it's about the midpoint. And draw a line that looks like it's making a right angle at that point. And if you really did it with your compass and a protractor and made sure that it was perfectly right angles, perfect midpoints, you actually constructed with your compass and ruler the perpendicular bisectors, then what you would see is that they all 3 intersect at a common point. If yours didn't, fudge it a little bit so that it does. Okay, it needs to intersect at a common point. It's just because you didn't really construct it so it didn't turn out perfectly. Okay, so what I've drawn here on the board are perpendicular bisectors. And again, what did we say we call these lines if they all intersect at a common point? Concurrent lines. And what do we call the point where they intersect? Point of concurrency. Now, that's general. If that point of concurrency is made by perpendicular bisectors, it has a special name. And that special name is the circumcenter. The circumcenter is the point of concurrency of the perpendicular bisectors. And we're going to learn 4 different points of concurrency. So this is our first one, the circumcenter. If you draw in the perpendicular bisectors, they will create a point of concurrency, and that point of concurrency is called the circumcenter. Following me so far before I move on? The circumcenter is the point of concurrency of the perpendicular bisectors. And when we get through next week learning all 4 of them, I will give you an acronym that will help you memorize, okay, that you can use. Okay, so now we're getting ready to learn our 3rd theorem for today, called the circumcenter theorem. So if you have a triangle, you've drawn in the perpendicular bisectors, you found the point of concurrency called the circumcenter. The circumcenter theorem says that the point of concurrency, the circumcenter, will be equidistant from the vertices of the triangle. Equidistant to the vertices. So in other words, if I draw in my picture the distance from the circumcenter to each vertex, from here to here, from here to here, and from here to here, all of those will be the same length. The circumcenter theorem says if you have perpendicular bisectors, and you're going to have to be able to tell by looking at the picture. So when you look at the picture, you're going to look at the markings. Perpendicular, bisected, perpendicular, bisected, perpendicular, bisected. You're going to notice that you have perpendicular bisectors. If you have perpendicular bisectors, which are the red lines, then where they meet, P becomes the circumcenter. And this theorem says that P to each vertex, PB, PC, and PA, will all be the same distance. Okay? So you're drawing the perpendicular bisectors through the sides. The circumcenter is not going to be equidistant to the sides because that's what you went through. It's going to be equidistant to the vertices or the angles. Are you with me there? Okay? That's the theorem, and then they're going to try to get you to understand some information about it. This will be huge for your always, sometimes, never questions on the Chapter 5 test. You may want to make a note. And again, next week when we've learned all 4, I'm going to give you an acronym that's going to help you with the always, sometimes, never as well. Okay? So, they have went ahead on this picture and created 3 different kinds of triangles, acute, obtuse, and right. In the picture, these red lines are supposed to be the perpendicular bisectors. They don't label that or show that anywhere on this page. So if I were you right now, I would go through and put the markings so you can see it. So if this is a perpendicular bisector, it should be making a right angle, and it should be splitting this side into 2 congruent parts. So I would mark that on my notes. This line should be perpendicular and bisecting this side. And then the third one should be perpendicular and bisecting the third side. So on every side, those lines, when they go through the side, should be perpendicular and bisecting. So one more time, what do we call this point P? The circumcenter. Okay? Where is the circumcenter when the triangle is acute? It's inside the triangle. That's the kind of question I'm going to ask you always, sometimes, or never about. If your triangle is acute, the circumcenter will always be inside the triangle. Okay? If it's obtuse, again, I would go to my picture and I would put those little right angle and marks to show that these are perpendicular bisectors. So on every side where the line crosses should be perpendicular and bisecting. This line is the one that's perpendicular and bisecting this side. And then this line is the one that's perpendicular over here on the hypotenuse. Well, it's not really hypotenuse since this is obtuse, but on that side, and it is splitting it into 2 congruent parts. Okay, and so what do we call point P again? I'm going to keep saying it till you memorize it. Circumcenter. And where is the circumcenter if the triangle is obtuse? Outside. Okay, and lastly, if it's a right triangle, again, I would put those markings on it. Perpendicular bisecting, perpendicular and bisecting. And then the last one here that's diagonally going through it is perpendicular and bisecting. And where is point P if it is a right triangle? It is on the triangle, and specifically it's on the hypotenuse. And then just to clarify one more time what the circumcenter theorem says. So in green, I'm going to write what the theorem says. The circumcenter theorem says the circumcenter will be equidistant to the vertices. So these will all be the same. You guys with me there? Equidistant to the vertices. So those will all be the same. Equidistant to the vertices. Those will all be the same. Okay? Everybody's head's wrapped around circumcenter made by perpendicular bisectors. All right. Last thing they're going to try to show you is why this is true. Why the circumcenter is equidistant to the vertices. So it brings up a new vocabulary word called the circumscribed polygon. So it says the circumcenter of triangle ABC is the center of a circumscribed circle. If you look at this picture, do you see how this circle is touching every vertex of the triangle? If the circle is outside touching the vertices, so if the circle contains the vertices, we call it circumscribed. Circumscribed. It's going around the outside of the triangle and it's touching every vertex. That's a circumscribed circle. Notice, if this is the circumcenter and the circumcenter is the center of the circle, what is this distance from the circumcenter to each vertex going to be in the circle? What is PB in the circle, or PC in the circle, or PA in the circle? It's the radius. And in a circle, what do we know about all of the radii? They're always the same length, right? In the same circle. So what we just learned was that the distance from the circumcenter to each vertex is the same. And that's because if you draw a circle around the outside of that triangle, those would all be the radii of that circle. Does that make sense? Okay, so this is the why the circumcenter theorem works. Okay, so then you're going to see a picture like this. They may or may not give you information. If they do, read the information, mark the picture. I can't stress to you enough. We are in section 5.2. By the time we get done with chapter 5, which has 8 sections, it's going to be tough because you're going to have all this information put together. Best thing you can do is read and draw your picture and mark your picture. So it says DG, EG, and FG are perpendicular bisectors of the triangle. So I'm going to find those line segments and I'm going to mark perpendicular and bisecting. So DG is perpendicular and it's a bisector of the triangle, meaning it's bisecting the side of the triangle. So DB and DA should be congruent. Again, I'm giving you advice. Some of you are taking it, some aren't. I would mark my picture. EG. EG is a perpendicular bisector, so it's perpendicular and it's bisecting. So we would mark the side split into 2 congruent parts. FG is a perpendicular bisector, it says. So again, it's perpendicular and it's splitting the side into 2 congruent parts. If you'll mark the picture with what it gives you, then answering the questions will be really easy. The other thing we learned is that if this is a perpendicular bisector where they cross at point G, what do we call point G? Circumcenter. And what did we just learn about GB, GA, and GC? They're all the same. So we could mark those congruent. And now we shouldn't have any trouble answering some questions about this picture. So the question they ask first is, what is GC? So what's the distance from G to C going to be? It's going to be the same as GB, which is 13.4. So it's really easy to answer the question once it's marked. Okay, I'm not going to change my picture because it's all marked here. But if you look at the next example in your notes, it's the same picture, right? But what does it ask you to find this time? Say it one more time. JZ. Does everybody agree? We're on. I think that's the one below. Sorry, I'm going to come back to that one, Weston. What's the one to the right? GK, okay? So the next one asks you to find GK, but I'm not going to flip my slide so I can still have my picture marked. So GK, oh, it's not the same picture, is it? I'm so sorry. JZ are the same picture? Okay, thank you, Cooper. All right, so I am going to switch this. Let's remark our picture. So on this one, they tell us KZ is a perpendicular bisector. Did I give you guys that information? No, write this sentence down. You could not do this problem without it. So KZ is a perpendicular bisector of triangle GHJ. You have to have that information before you can answer the question. Okay, I'm going to go a little quicker this time. So KZ is a perpendicular bisector. So in my picture, that means it should be perpendicular to the side of the triangle, and it should be bisecting the side of the triangle. And what do they ask us to find here? GK. So now to answer this question should be really simple. What is GK going to be the same as? HK, which is 18.6. If you go on to the next question, which is the same picture, it doesn't give you any other information, but it just says find what? JZ. Okay, so if we go to the picture, JZ, we're looking for this distance right here. That's from point Z to the vertex. Remember what we talked about though. If KZ is a perpendicular bisector and it intersects this line LZ and this line MZ all at point Z, what is that making point Z? The circumcenter. And so the circumcenter is supposed to be equidistant to where? All the vertices. So ZJ, ZH, and ZG. So what is JZ going to be the same as? 19.9 GZ. So this is going to be 19.9. So again, the math shouldn't be difficult. It's can you mark the picture with the correct theorem information. If you can mark your picture, then it's really easy to answer the questions. The only thing I would warn you about when you get to the homework tonight is that there will be some questions that might make you go back to Pythagorean theorem. So if you get stuck on a problem, look and ask yourself, do I have a right triangle in my picture? And if you do you have enough information then maybe to use Pythagorean theorem to find a missing side length? Because there are a couple problems where it might get a little bit more challenging, and the part that makes it more challenging is they don't give you one of the sides, but they gave you the other side, and you can use the Pythagorean theorem to find it. Does that make sense what I'm saying? Okay. All right, so if we move on to the next one, I'm going to come back to this graphing one, which I think is next, right? Is there a graphing one next? Okay. No? Yes? Okay. I'm going to come back to it, if I can get there. My computer's going slow. I want to get to the last theorem to make sure I don't run out of time, and then we'll come back to the graphing parts. Okay, so I want to get to here. This is the next slide after the graphing, right? Come on, guys, talk to me. We have very little time left. After that graphing example, is this what's next in your notes? Okay, stay with me. All right, so it says a triangle has 3 angles, so it has 3 angle bisectors. I already told you that. So we're back to this last theorem we talked about in 5.1. We're now going to apply it to our triangle. A triangle has 3 angles, so it's going to have 3 angle bisectors. Just like with the perpendicular bisectors. If we draw a triangle, so right now on your paper, draw yourself a triangle. Estimate where you think the angle bisectors would be. So just draw a line going through the angle that would split each angle into two congruent parts. Do that on every angle, but keep in mind that if you really do this correctly with a protractor or with a compass, depending on whether you measured it and split it or you did it with a compass and constructed it, you should have them intersect at the same point. So you may have to fudge yours just a little bit since we're not taking the time to really construct them. But we reviewed how to construct them in BOWORK. So you could construct the angle bisectors, but pretend that they perfectly intersect at one common point because they should. Okay? So connecting all this together again. 3 lines that intersect at a common point, what do we call the lines? Okay, you're talking about the point. What do we call the lines? Concurrent lines. Where those 3 lines intersect is called a what? Point of concurrency. So if I'm drawing in all of the angle bisectors, then where they meet is the point of concurrency, right? In this problem made by angle bisectors, that point of concurrency is our second special point, has a special name. It's called the incenter. So circumcenter is perpendicular bisectors. Incenter is the point of concurrency of the angle bisectors. Okay, point of concurrency of the angle bisectors. So we're going to call this point right here the incenter. All right, incenter theorem. Last theorem for today. So 4 theorems you're learning today. The incenter theorem also says that the incenter is going to be equidistant to something. But it's the opposite location of where the circumcenter is equidistant to. The circumcenter was equidistant to the vertices, right? The incenter was made by going through the vertices. So it's not going to be equidistant to the vertices. It's going to be equidistant to the sides. Okay, so if I draw this in, I'm going to go from the incenter over to each side, but I'm always going to draw that perpendicularly. So this distance, and this distance are going to be the same. Here, here, and here. Drawn perpendicularly. So if you look at the board where the theorem is, and then we're on 5-2 towards the end. Okay, so everybody look up here with me real quick and let's make sure you understand this picture. What are the red lines showing you? Angle bisectors. Where they meet is this point P in the middle, right? And what is that called? Incenter. And this theorem says the incenter, which is made by going through the vertices, is not equidistant to the vertices. It is going to be equidistant to the sides. And when you draw those distances, they have to be drawn perpendicularly. Here's how I keep them straight. If I go through the sides to get my point, perpendicular bisectors go through the sides, right? Then that point's going to be equidistant to where? The angles, the vertices. If I go through the angles by drawing an angle bisectors to get my point, it's going to be equidistant to the sides. Does that help? Okay, so you have 2 points of concurrency today, the circumcenter and the incenter. The circumcenter is equidistant to the vertices. The incenter is equidistant to the sides. So now we look at another example or another situation, just like the always, sometimes, never. So again, this will be always, sometimes, never on your test. So be prepared. And again, these red lines, just to save time here, I'm going to say that the red lines are angle bisectors. Okay, so each of these points P's are called what again? Incenters. So each of those are the incenter. Okay, where is the incenter always going to be if it's acute? Inside. Where's the incenter going to be if it is obtuse? Inside. Where is the incenter going to be if it's a right triangle? So unlike the circumcenter, the incenter is always inside, no matter what kind of triangle it is. Okay? And then we're going to look at why the theorem works again. So I told you first we had a circumscribed circle which went outside the triangle and touched the vertices, right? That was for the circumcenter theorem. If your circle's inside the triangle, it's called an inscribed circle. The circle is considered inscribed if it intersects the polygon on each line that contains a side of the polygon. It's really wordy. So what it means is if you look at one side, the circle is going to touch the sides of the polygon. Look at another side, it touches the side of the polygon. And then the third side, it touches the side of the polygon. So if your circle is inside, it's inscribed. Or it touches the sides of the triangle. If it touches the vertices, it's circumscribed. So notice what happens if I look at it as an inscribed circle, and this is the incenter. We said the incenter is equidistant to what? The sides. So if I go from here to the side, perpendicular, here to the side, perpendicular, here to the side, perpendicular, what do those all turn out to be in that little red circle? The radii. And all radii are equal. Okay, so again, an inscribed circle proves why the theorem works. A circumscribed circle proves why the circumcenter theorem works. Okay, so last example besides the graphing questions I want to go over. There should be 2 examples left, right? So, and we only have about 2 minutes because we're on RTI today. So I'm going to try to go through this really quickly, but here's what's going to happen. I'm going to send out a link to a video that's going to have how to work the graphing question and whatever we don't get to here. And you're going to need to watch a short little video over how to graph and how to do this on Friday. You can do it at home tonight, tomorrow night, or on Friday during class, and then you'll be able to finish the entire assignment on Friday. Are you guys with me? Okay, so let's look at least this one before we stop. So MP and LP are angle bisectors of triangle LMN. So again, I would mark my picture as soon as I read that. MP is an angle bisector of the triangle. LP is an angle bisector of the triangle. So it's bisecting the angle of the triangle that it intersects. What does that make point P? The incenter. It asks you to find the distance from P over to line MN. How do we always draw distance from a point to a line? Perpendicularly. So they want to know, what is that length? We learned that the incenter is equidistant to the sides. So that means the distance from P over to this side in red should be the same as the distance from P over to this side, PQ. Do you see how those should be the same? And what is PQ? 5. So what is the distance from P to MN? 5. Okay, we didn't get to the last one or the graphing one, so I'm going to do a short little video today before I leave. I will save that and I will send it to you through Remind. Anybody in here not signed up for Remind? Okay, so you're going to get that video sent to